Okay, this is the first section on intersecting lines. These are two lines that are going to cross each other. And we'll have a quick discussion later of what happens if they are crossing but don't meet. It's also possible that if these two vectors that are pointers, if they're parallel, it's possible that the two vectors may not cross at all, and you'll get some weird effects, and we'll have a look at an example like that as well on this. So this is the example from the book. This one will definitely cross. Let's have a look and see what happens when it does and how we solve it. So we can write this whole equation as one vector equation on the left hand side. There's 3 plus lambda, 1 minus 2 lambdas, and 1 minus a lambda. And we are saying that when these intersect, the two vectors R1 and R2 must be the same. So we're going to equate the two vectors. We've got minus 5 mu, or 0 minus 5 mu, minus 2 plus mu, and 3 plus 4 mu. The I, J and K parts must independently all solve with the same values. So what we often do is you quickly look at which pairs you think you can solve together. So we've got the I, the J and the K. And I'm going to solve I and J together. So I got a pair of simultaneous equations, 3 plus lambda equals minus 5 mu, and 1 minus 2 lambda equals minus 2 plus mu. Solve them simultaneously. So is it worth multiplying? Let's double the first equation. So 6 plus lambda, 2 lambda equals minus 10 mu. And 1 minus 2 lambda, let's bring the minus 2 across as well. So we've got 3 minus 2 lambda is equal to mu. If we add the equations together, we're going to get 9. The lambdas have disappeared, equals minus 9 mu. So mu equals minus 1. Put that into one of the other equations. First of all, we put them into the same two equations above. So let's say 3 plus lambda equals minus 5 times minus 1. That gives me lambda is 5 minus 3, lambda is 2. That's correct for should be correct for both I and J. So that's the I and J parts where they cross over each other in I and J. We've now got to check, do they meet at K as well? So we check that by putting it into the equation. 1 minus lambda, does it equal 3 plus 4 mu? We'll stick our numbers in. So we've got 1 minus 2, does it equal 3 plus 4 times minus 1? That's going to be our minus 1, and this equals minus 1. So yeah, match. So that means that I, J and K are all solved simultaneously. So the lines meet and cross. If they hadn't, say this last one had been a 4 on this point, that would have been 4 there. And when we came to solving this last bit, that would have been a 4, minus 4 would have been 0. These two things don't solve. So if we can't solve for that one, what happens is we get, if K doesn't match, that would actually say not crossing. Well, not intersecting. What can happen is you can have one vector going R1 another vector going R2, and at some point they've got the same I and j, but the k's don't match. Okay, so that's possibly 1, 1, 0, and that could be 1, 1, 1, and therefore they're not actually meeting in space. One's crossing over, they're crossing, but they're not intersecting. That's the alternative solution to that. This one gives this. And the second one is if the k doesn't match, they're not intersecting. So let's just have a look at these two vectors. This is the given in the problem, and that's where they cross, and see they cross and meet at a point. And I said if my x value on this one had been slightly different, if I'd said 4 here, why is that not changing? 3, what's that line? Let's turn that off. And if I just move this point up, so it's 4. See the equation. Problem was the way the equation gets recorded when they do this. So I've just edited this one to change the 3 to a 4, press enter, and notice now the two vectors don't intersect with each other. Okay, there's one other case that we're going to look at in a few moments. But there is a question still not answered, and that's if we go back to where they do intersect, where do they intersect? So let's go and do that bit. And the way to find out where they intersect is we take our values of mu or lambda, doesn't matter which one, and we put it into the relevant equation. So to find the intersection, I'm going to say mu equals -1, and my mu equation is 0, -2, 3. Add on mu, -5, 1, 4. And I'd put -1 in here, we get 5. -2 minus 1 is -3. And 3 plus -4 is -1. And that gives us the point of intersection. And if I just bring the graph back and put a point on that intersecting point, it seems to be crossing there. 5. -1 is plus, -3, yeah, 4 minus 1. Did I choose the right mu? Mu is -1. And let's put the point on. I'm just collecting the point, connecting it to put it. For some reason it's not wanting to do it on the intersection. I'll do it that way. So intersect between that line and that line. Get it off, I'll just want to do. Oh, this is the wrong form, that's why. Still wrong form. There we go. No, wrong form still. There's the equation where they meet. Let's put the point where they meet. And check the equations of the coordinates of that point. 5 minus 3 minus 1. There's the point that they intersected. And there's another case. From this point on, we're actually optional. They don't seem to talk about it in the book. but it's not much more, so this is optional. And we've got two equations now. First one is the same as the one we had before, 3, 1, 1 plus lambda 1 minus 2 minus 1. And my second equation this time, or my third equation I'll say, R3, is 3, 2, 1 plus lambda or mu, in this case, of 2 minus 4 minus 2. So let's see what happens when we try and make these two equations solve. So we're going to get our set of equations. All three of them are the same. So it's 3 plus lambda equals 3 plus 2 mu. We get 1 minus 2 lambda, and that equals 2 minus 4 mu. And if we do 1 minus lambda, and these, that equal to 1 minus 2 mu. And what we can find from this one, let's see what happens if we try combining equations. So let's add I to k. So we get 4 with no lambdas equals 4. So that's eliminated both lambda and mu at the same time. That sort of indicates that the lines are going to be parallel and possibly equal. Let's see what happens if we try adding 2 lots of I to j. So 2 lots of I, it's going to be 6 plus the j, so that's 6, 7. Plus 2 lambda minus 2 lambda is nothing. 6, so 8. And 2 mu minus 4 mu gives me no mu's. They cancelled as well. And we've now got a point where this is incorrect. So the fact we keep losing all our lambdas and mu's says they're parallel. The fact that we get an incorrect statement at some point says they are only parallel and they are not the same. So this is just a special case of you can't get solutions. And if you can't get solutions for these two equations of a line, they are actually parallel lines that do not intersect. If I actually put this back to 1, you'll find, and I can't change it to 1 there, but if I change that to 1 in here, you'd find that all of these would, this would have cancelled down to being 0, down to 7 equals 7 as well. And all our equations would give us truthful statements, then it says that it's true for all values. Okay, so if I'd actually said R4 is 3, 1, 1 plus mu 2 minus 4 minus 2, we actually realise they've got the same starting point. They've got parallel vectors because they're multiples of each other. The only thing changing is the value of the lambda. And in this case, all of these statements would work out as being true, and that would actually mean that R1 is actually equivalent to R4. They are the same line. Okay, so that's equations of a line.